Good morning/afternoon. Today, we're diving into the origins of Hadoop, a technology that fundamentally reshaped how we handle massive data. We'll explore not just what Hadoop is, but crucially why it emerged and the profound problems it solved. This journey starts in the early 2000s, a period of unprecedented data growth that pushed existing technologies to their breaking point. Before we get into the technical specifics, let's frame why understanding Hadoop's history matters. Hadoop wasn't created in a vacuum. It was a direct, ingenious response to a crisis faced by early web giants. Its development sparked an open-source big data revolution, enabling technologies we rely on today for analytics, machine learning, and data lakes. By understanding its origins, the specific pain points, and the breakthroughs that address them, we gain deeper insight into its core design principles and its lasting impact on modern data infrastructure. The catalyst for Hadoop was simple: an overwhelming flood of data. Picture the early days of Google, Yahoo, and Facebook. User bases exploded, web pages multiplied, and interactions generated logs at an unimaginable scale. We're talking about data volumes leaping from terabytes, which was already challenging, into entirely new territory, petabytes. To put this in perspective, a petabyte is 1,000 terabytes, or 1,000,000 gigabytes. Think billions of web pages, trillions of user clicks, massive logs. This wasn't just growth, it was a data explosion. Crucially, the workhorse of enterprise data up to that point, a traditional relational database management system, or RDBMS, simply couldn't cope. Scaling these systems vertically, meaning adding bigger, more expensive servers with more CPU, RAM, and storage, hit physical and financial limits. The cost to store and process a petabyte in an RDBMS was astronomical and practically infeasible. The existing paradigm was breaking. This data explosion exposed three fundamental, interconnected challenges that existing systems couldn't overcome. Storage limits. Vertical scaling, buying bigger, more expensive servers, was the traditional answer to needing more capacity. But this approach was hitting a wall. It became prohibitively costly to keep buying the biggest possible machines. More importantly, it was incredibly inflexible. Adding capacity meant significant downtime and complex migrations, and there was a hard physical limit to how big a single server could get. The data volume was outgrowing this model. Processing bottlenecks. Even if you could store the petabytes, how do you process it? Single-node systems relying on one powerful computer were completely overwhelmed. Running complex analyses like building search indexes or calculating user behavior trends on petabytes of data would take weeks or months, making timely insights impossible. The compute power needed dwarfed what a single machine could provide. Fault tolerance. This is critical. To handle petabytes, you must use hundreds or thousands of relatively cheap, commodity servers instead of a few expensive ones. But in such large clusters, hardware failures, a dead disk, a faulty network card, a blown power supply become a daily, even hourly occurrence, not a rare event. Existing systems weren't designed to handle this constant churn. A single failure could crash a long-running job, making large-scale processing unreliable and impractical. These three challenges, storage, processing, and fault tolerance, created a perfect storm. The web giants needed a fundamentally new architecture. Enter Google, facing these challenges at the extreme scale of their search engine. They didn't just complain, they invented solutions and, crucially, shared the core concepts with the world through seminal papers. Google File System GFS 2003 ***. This paper described a revolutionary distributed storage model. Instead of one big disk, GFS split massive files into chunks, typically 64 MB or 128 MB, and replicated those chunks usually 3 times across many cheap servers. A master node kept track of where everything was. This provided massive, scalable storage and built-in fault tolerance. If one server died, the data was still available on others. MapReduce 2004. This paper described a programming model for parallel processing of vast datasets across thousands of machines. It abstracted the complexity. Developers wrote simple map and reduce functions, and the framework handled parallelization, distribution, task scheduling, and crucially, fault tolerance, automatically restarting failed tasks on other nodes. Together, GFS and MapReduce formed the blueprint. They demonstrated a practical way to store and process petabytes reliably on commodity hardware. These papers didn't release code, but they ignited the imagination of the open-source community, proving it was possible and outlining how. The spark from Google's papers landed in the Nutch project. Around 2002, Doug Cutting and Mike Caffarella were building Nutch, an ambitious open-source search engine. Their goal was immense: to crawl and index the entire web over 1 billion pages, something only well-funded giants like Google were achieving. They quickly hit the same scalability walls. Storing and processing billions of web pages required a distributed approach. Inspired by the GFS and MapReduce papers, Cutting and Caffarella began implementing similar concepts within Nutch. They created the Nutch Distributed File System, NDFS, as their open-source answer to GFS, and they implemented a MapReduce execution engine. This was the crucial incubation period. Nutch proved the concepts could work outside Google and provided the initial open-source codebase for distributed storage and processing. 2006 marks the official birth of Hadoop as we know it. Doug Cutting joined Yahoo, a company desperate for a solution to its own massive data problems. Recognizing the broader potential beyond just search, the NDFS and MapReduce components were spun out of Nutch into a separate, independent project named Hadoop. Their name? A charming anecdote: Doug Cutting named it after his young son's yellow toy elephant. Yahoo provided massive resources and a real-world testing ground. By 2007, just a year later, they were running Hadoop on a 1,000-node cluster, demonstrating its viability at an unprecedented production scale for open-source big data processing. This was the moment Hadoop stepped onto the world stage. With a solid core HDFS for storage and MapReduce for processing, Hadoop exploded into an ecosystem. Key milestones. 2008, Hadoop graduated to become a top-level project within the Apache Software Foundation, signifying its maturity and importance, and accelerating community development. 2009, a dramatic demonstration of speed. Hadoop sorted 1 terabyte TB of data in just 62 seconds. This shattered the previous record of 297 seconds set by a proprietary system, showcasing Hadoop's raw processing power on commodity hardware. Tools proliferation. Recognizing that not everyone wants to write Java MapReduce code, powerful tools emerged. Hive, developed at Facebook, brought familiar SQL-like querying HiveQL to Hadoop data, opening it up to a vast pool of analysts. Pig, developed at Yahoo, provided a high-level scripting language, Pig Latin, for expressing complex data flows and transformations. HBase, modeled after Google's Bigtable, offered a NoSQL, column-oriented database on top of HDFS for real-time read/write access. This period transformed Hadoop from a powerful engine into a versatile data platform. Hadoop moved from web giants and pioneers into mainstream enterprise adoption. Hadoop 2.0 2012, a watershed moment. The introduction of yet another resource negotiated decoupled resource management from the MapReduce processing engine. This meant Hadoop could now run diverse workloads like interactive SQL via test/lab, real-time streaming Storm, latest Spark streaming, graph processing Giraffe, and machine learning MAT efficiently in the same cluster alongside MapReduce. Yarn unlocked Hadoop's potential as a true multi-workload data operating system. Cloud integration. Major cloud providers launched fully managed Hadoop services: Amazon EMR Elastic MapReduce, Microsoft Azure HD Insight, and Google Cloud Dataproc. This drastically lowered the barrier to entry, allowing enterprises to leverage Hadoop without managing physical clusters. 2020's cloud-native shift while HDFS and MapReduce concept remained foundational, the trend shifted towards cloud-native architectures. Technologies like Kubernetes for container orchestration, Cloud Object Storage S3 ADLS GCS replacing on-prem HDFS in many cases, and serverless computing started to influence how large-scale data processing is deployed and managed. Hadoop distributions evolved, and newer engines like Spark often run alongside or integrated with cloud-native services. Hadoop's impact is undeniable and far-reaching. Democratized big data, it proved you could reliably store and process massive datasets using inexpensive, commodity hardware. This shattered the cost barrier, making big data analytics accessible far beyond the largest tech companies. Powered the modern data stack, it is the foundation of the modern data lake concept. It enables complex analytics batch and increasingly interactive and large-scale machine learning pipelines on raw, diverse data. Inspired a generation, Hadoop directly inspired faster, more flexible processing engines like Apache Spark and Apache Flink. Its concepts heavily influenced the design of cloud data platforms BigQuery, Redshift, Snowflake, Synapse, and managed services. enduring core concepts. While specific implementations evolve, the core architectural principles pioneered by Hadoop, specifically HEFS-like distributed, fault-tolerant storage and the MapReduce paradigm for parallel processing, even if executed by newer engines, remain absolutely fundamental to virtually all modern large-scale data systems. Hadoop didn't just solve a problem, it defined a new paradigm for data at scale.